Alright, so this quick tutorial will go over ionic and covalent compounds and bonds and how their names and how you can find their names and formulas, how you can get those, because I know that might be something that some people are confused on. So we're just going to start with a review on what ionic and covalent bonds slash compounds actually are. So in ionic bonds, these occur between, as you can see, it's written here, a metal and a non-metal. So, for example, like sodium and chlorine. Sodium is a metal, chlorine is not a metal, and that's how you get NaCl. We'll go on to that as an example later. And just know that it's the giving of electrons or the transaction of electrons. So one element, one atom will be giving electrons, and the other element will be accepting it, or the other ion will be accepting them. So that's that. Now in covalent bonds here, just note that it's between a nonmetal and another nonmetal. So an example might even just be water. It's H2O. Hydrogen is a nonmetal. Oxygen is also a nonmetal. That is actually an example of a covalent compound, covalent, bond. And just know it's the sharing of electrons. So the elements will share them instead of giving them. So that's a really quick review on those two things. Now let's move on to naming. So on naming, we're going to start with ionic. Now on ionic, there are like two different types of ions you need to know that might be helpful. First kind is monatomic ions. So this example here, like the first definition I'm giving here, is for monatomic ions. Monatomic means one atom, and then the other kind of ion is a polyatomic ion. Polyatomic meaning many atoms. So we're just going to start off with basic monatomic ionic bonds, which are like probably the easiest, most simple ones. And in these, and in general for ionic bonds, you're just going to want to keep the first element as simply just that name, the name of that element. For the second part of the name, you're just going to want to put the element name and the "-ide" suffix, and that's basically it. Another key pointer you need to know about naming ionic compounds, which is listed down here, I think somewhere here, this key tip here. Remember, the two components of the ionic compound, whether monatomic or polyatomic, must have canceling charges. In other words, these charges in an ionic bond, they must cancel each other out. You need to know that they must cancel each other out. So in the first example, we have Na, and we have sodium here, Na. We have chlorine, which is Cl. Sodium is an alkali metal in the first group, and it has a +1 charge as an ion. Chlorine is in the halogen group, and it has a -1 charge. So the charges are balanced, as you can see. +1, -1 cancel out, so there's not going to be no balancing is going to be needed. So the name is simply just going to be sodium, taking this first name here, and then you take chlorine, remove the "-ine" at the end, and add "-ide." So the name is sodium chloride. Another example is down here. We have calcium, which is a alkali earth metal group 2. As an ion, it has a +2 charge. Then we also have sulfur, which is a nonmetal, and as an ion, it has a -2 charge. So as you can see here, the charges are canceled out, right? As you can see, they're balanced, which is good, meaning no balancing is going to be needed. And the name is simply just going to be calcium and sulfide. That's, yeah, calcium sulfide here, as you can see. You move the sulfur, you move the at the end and add "-ide, and you're pretty much good to go. Now for polyatomic ions, if you remember that long list of those random ions like phosphate and peroxide, nitrite, that's what we're dealing with here. Now, just to know, polyatomic ions are a charged group of 2 or more elements or bonded atoms that can be considered a single ion. And naming is similar as before. So here we have the example of magnesium and this CO3 here. As you can see, CO3 is not an element. Do not confuse this for an element. Don't call that an element because it's not. It's actually 2 elements. It's carbon and oxygen, as you can see there. But it's a polyatomic ion, as the definition above describes. It is, although it's a charged group of two or more atoms, bonded atoms, or like, elements, we consider this whole thing as one unit, and the charge applies to this whole thing as one unit. It's considered a single ion. So now that we know that, magnesium, if you look, it's an alkali earth metal. It has a +2 charge. CO3, if you look through your list, this might take a while, but I already found it. It is carbonate. Okay, now look at the charges, because we have to make sure they cancel out. If they don't cancel out, we're going to have to do balancing, which I will describe in other examples later in the video. We have +2, -2, perfect. They completely cancel each other out, so then the name is just going to be magnesium, and then you just magnesium, magnesium. And you don't do any carbonide or something like that. You just take carbonate, and that's the end answer here. Magnesium carbonate, that's it. We'll take another example here. We have lithium, okay, perfect, and we have our polyatomic ion here. So lithium, we know, is an alkali metal. It's in the first group, and as an ion, it has a +1 charge. Now this second component here, NO3, that's a polyatomic ion, as it's composed of two or more elements, which are considered as one whole unit of an ion. Now we look through our list, find NO3, we find that to be nitrate. And if you also look, it'll tell you it has a charge of -1, which I've written up here for you. Again, these are equal. These cancel each other out. +1 cancels with -1. Perfect. No balancing needed. And your name will simply just be, again, as before, lithium, nitrate, and we're done. That's your answer right there. Perfect. Now we're going to go on to naming ionic compounds with transition metals. Those are the middle ones, the elements in the middle of the periodic table, like titanium, vanadium, chromium, manganese, iron, all of those. Again, I just put this reminder tip here. Remember that the two components of the ionic compound, again, whether monatomic or polyatomic, must have canceling charges. So this is going to be you're going to need to know that as you do these problems with the transition metals, because the thing about transition metals is that they can form different kinds of ions. If you look at your periodic table, that sheet of ions that the periodic table of ions sheet that we have, let's take iron, for example. It shows that it can have a +3 charge or a +2 charge. So how do you know which one to use? That's where we're going to have to make sure we pay attention. So we're going to use examples to kind of explain this. Here we have titanium. Here we have nitrogen. There are no subscripts or anything like that, so it's just a single titanium atom and a single nitrogen atom, okay? Now, if we look at nitrogen on the periodic table as an ion, it is a -3 charge, which I've written up there. Now, titanium, it is going to be a plus something charge, but I put a question mark because it can be two options. It could either be 4+ charge or 3+. We don't know because we have to figure that out. Now, if we see there's only one of each atom, then what ion would it need to be in order to cancel out with this one? It can't be 4, because if this was a 4 and 3 don't cancel out, do they? They need to cancel out. So which means that this titanium here, it must be titanium 3, which is why I've written a 3 here, and that's how we got this answer here. The end part just uses that "ide" suffix again, unless you're using a polyatomic ion, which we get on to an example down here. But unless it's a polyatomic ion, you again just take off the ending and add "ide." Nice. That's how you're going to need to go about it for the transition metals. Now we have another example of a transition metal thing here. This one's going to be a bit more complex. So we have copper, and notice the subscript 3, which means we have 3 of these copper atoms, okay? We have PO4. Let's find out what that is first. PO4 is apparently, it's phosphate, as I've written down there, but if you look through your the table of polyatomic ions on your periodic table, it'll tell you that it is phosphate. If you look at the charge, it is -3. Okay, what else does it tell? This subscript 2 tells us there are two of these atoms, right? Two of these polyatomic ions right here. So if the original single unit has a -3 charge, and there are two of those -3s, that means this thing as a whole has a -6 charge, doesn't it? Because there are two of these -3s, right? So it's a -6 charge. Nice. So I'll just keep that there as a reminder. All right, now let's look at the copper. Copper, according to our periodic table, can have an ionic charge. It can be +2 or just +1. Which one is it? Now, this is where we have to use our brains a little bit. So, use our brain a little bit. So, if you look at this 3 here, that means there are going to be 3 of these copper ions, right? And we know that it must balance out with this -6 here. So, which one could it be that if there are 3 of them, it turns out to be +6 in order to cancel out? Well, let's test it one by one. Let's see if it's copper 2 with a 2+ charge here. Well, if there are 3 of these +2s, then you come out to +6. These two cancel out, don't they? Which means that must be the answer. Great. However, let's try the other one just in case. If we take copper 1 that had a +1 charge, there are 3 of these copper ones here, which means that it has a 3+ charge. Now, these don't cancel out, do they? So that means that is not the answer. So based off a little bit of reasoning, we can find out that this copper must be copper 2. Or actually, we have to write in Roman numerals, so it must be copper 2. And we found out this to be phosphate, so now the answer is just going to simply be copper 2 phosphate. Phosphate because of this ending right here, and 2 we found out through our reasoning by finding what version of copper it must be in order to cancel out and balance this entire thing. Because remember, these two components must balance each other out in all circumstances. All right, now we're going to move on to naming covalent compounds. Now these are a lot easier than the first one, in my opinion anyway. So what you're going to want to do is, looking at the formula, you're going to want to use the proper prefixes plus the name of the element. Yeah, and then on the second element, make sure to also include "ide." So we're going to look at this example here. We have OF2, so we have oxygen, and we have fluorine. F is fluorine, O is oxygen. Now, to name it, it's going to be pretty simple. You're just going to put oxygen, and then you're going to want to find the prefix. Since it is 2 here, that means there are 2 fluorines. And if you look through your list of prefixes, that translates to di. Di is the prefix for 2. So it'll be oxygen difluoride, because remember, you have to add "ide" at the end. Now you might, and also remember that for the first element, if it is a 1 here, or in other words, if there's 1 of that atom, do not put mono. Mono is the prefix for 1, but you never put it for the first element. So this will just say oxygen difluoride. Don't put monoxygen difluoride. That is not the right answer. This is how you're supposed to write it. Okay, now let's look at another example here. We have P2O5, P is phosphorus, O is oxygen. We have 2 of these phosphoruses, so we put diphosphorus, di meaning the di prefix meaning 2, pentoxide with the pent prefix meaning 5. And yeah, that's it. That's your answer. Here we didn't put mono because that is the one exception. You cannot put mono in the first element. You cannot put the mono prefix in the first element. So that was how you find the names. Now we're just going to go in reverse this time and try to find the formula from the name. So for ionic compounds, you're kind of just going to want to work backgrounds, and that's kind of vague, but it involves some reasoning. And just remember that your end goal, your objective, is to equalize the charges. That is your number 1 goal here, right? We have lithium chloride, okay? Lithium, all right, let's do a background check on lithium first. So we see that it's a alkali metal, and it has a +1 charge as an ion, so that's good to know, lithium. Chloride, this stems from what? Chlorine, doesn't it? Now, if we look at chlorine, it has a -1 charge. These two cancel out, don't they? +1 and -1 cancel out, which means no balancing is needed, which means the formula is just LiCl, simple as that. The Li has a +1 charge, the Cl has a -1 charge, they cancel out, this formula is correct. These charges on the top here, you don't need to put them, I just put them there to show you that the charges cancel out and that this is the answer right here. But yeah, in reality, you would probably just want to put LiCl. You don't need to put those charges at the top. Another example, potassium sulfide. Okay. So first we're going to look at potassium. We see it's an alkali metal in group 1. It has a -1 charge as an ion. Good to know. Now we look at sulfide. This stems from sulfur, right? The sulf, you can tell it's just going to be sulfur. Now if we look at sulfur on a periodic table as an ion, it has a -2 charge. Thing is, hold up, this is incorrect here. This is not a minus, this is a plus. If I did say minus anywhere in this video, that is about this potassium, that is incorrect. It is a plus, sorry. Oh my goodness. All right, there. If you look here, this +1 and this -2 don't cancel out, right? So we're going to need to balance this equation in order to make it so that way these two cancel out. In other words, how many of these potassium atoms do we need so that way it can cancel out with one of these sulfide atoms? Not necessarily one, but how many are we going to need of this to cancel out with this? This, again, has a -2 charge. This has a +1. So we're just going to need, if you think about it, you're just going to need 2 potassium atoms. That's why I put a K2S. If we look at it, potassium has a +1 charge normally, but since there are 2 of them, it now has a +2 charge, if we're considering, both potassium atoms. Sulfur has a -2 charge, and these cancel out then, don't they? That's how it works. You kind of got to work backwards. The other way you could do this is the crisscross thing. This is very similar. If you look at this K, how the crisscross works is that you take your element, write their charges, and then you just crisscross the numbers on both sides. And if you do it that way, it actually comes to the same thing. If you crisscross it, it becomes K2S1 or just, or just S, which is the same thing we got up here. You can do that crisscross method if you like that more. It may be faster for you, or you can work it out logically, whatever way works for you. Now we're going to go on to a bit more of a higher example, more difficult example. Higher, it's not even a proper word. Difficult example. So we have strontium, that is a group 2 alkali earth metal. It has a +2 charge. Nice. Phosphate. That is not an element on the periodic table. That is actually a polyatomic ion. If you search through your list of polyatomic ions, you find phosphate to be PO4 3-. Now, we just need to know that it has a 3- charge. Strontium has a 2+ charge. Okay. Clearly, these are not balanced. +2, -3. How many strontium atoms and how many phosphate ions will you need so that way these can become balanced? Well, if you take 3 of these strontiums and 2 of these phosphates, let's do it for one by one. 3 of these strontiums, all right, 3 plus 2s becomes +6, right? And if you take 2 of these -3s, it becomes -6. -6 and +6 cancel out, which means that that's going to be our formula. I don't know where this M went. Let me put it back. That's the formula, and that's what I've written here. Sr Phosphate, the formula, as I just mentioned earlier, it's PO4. Remember to put it in parentheses. For your polyatomic ions, make sure to put it in parentheses to show that it is a polyatomic ion indeed. So strontium, you're going to need 3 of them and 2 of these phosphates because phosphate has a -3 charge. If you take 2 of those -3s, you get -6. Strontium has a +2 charge. If you take 3 of those +2s, you get +6. +6 and -6 cancel out, which means that is your answer. Again, if you want, you can try the crisscross thing. This might be faster for you. Just write the SR 2 plus, write the PO4 3 minus. Now all you need to do is crisscross them. Then you get SR3 PO4. Oh god, this is hard to write. 2. Sorry for this horrendous handwriting, but I think you can get the point. You just crisscross them on both sides here, and then you'll also get your answer that way. We'll do a last example of trying to find the formula from an ionic compound by using a transition metal. Now this is going to be, actually this won't be too hard because in all the examples in which you have to find the formula, it will most likely give you the Roman numeral, which will indicate the charge, right? Nickel, this is a transition metal, right? It can be +2 or +3, but it tells us right here, and it will in most cases, that it is going to be a +2 charge because of the Roman numeral 2. Pyrophosphate, this is actually a polyatomic ion. If you look through your list of polyatomic ions, pyrophosphate has a -4 charge. These two are not equal. -4 and -2, or sorry, -4 and +2 do not cancel out, so we're going to have to do a bit of balancing here in order to make them cancel out. Okay, this is a -4 charge. This is a +2. How can we balance this? Well, if you take 2 of these nickels, 2 of these +2 charges, then it'll become +4. And if we just keep one of these pyrophosphates and just keep it -4, -4 and +4 now cancel out, which is great. And that is what we do here. It looks like somebody has deleted my work. There. So we have nickel normally has a +2 charge as indicated in the Roman numeral over there. And pyrophosphate, if you look through our list of polyatomic ions, it has a formula of P2O7, which I just wrote right there. And the charge on that is -4. Since we have 2 of these positive 2s, it becomes +4, +4, -4 cancel out. Again, when writing the formulas, don't include the charges. You don't need to, so don't do that. I just put it there so you can see that. So in reality, if you wanted to put that on a test, you'd probably want to put Ni2 and then P2O7 without the charges at the top. Now for covalent compounds, if you want to find the formula, this is even easier. You just have to use the prefixes and the element names to write the formula. You look at the prefixes, look at the element name, and then just write the formula. So we have carbon tetrafluoride. There is no prefix before carbon, and it is the first element in the series, first element in this compound, which means it must have a single atom of carbon. Tetra, that prefix indicates 4 atoms. So this formula is simply going to be CCl4. That's it. C for carbon and Cl for chlorine. 4 chlorines, 1 carbon. So really you could put a 1 next to that carbon if you wanted to, but that's not necessary. Another example, dinitrogen trioxide. So the di prefix on the nitrogen indicates that there are going to be 2 atoms of nitrogen. The tri on the oxide is going to tell us that there are going to be 3 atoms of oxygen. Again, make sure to look at this oxide nitrogen. That'll tell you which element it is. So it's dinitrogen, so 2 nitrogen, okay? That's what I got here. Trioxide, so 3 atoms of oxygen, so that's what I wrote there. And that is simply your formula, N2O3. And that is pretty much it for this video on how you name and find the formulas for ionic and covalent compounds.